This lecture is on NMR Spectroscopy, Part 1. NMR stands for Nuclear Magnetic Resonance. NMR spectroscopy detects nuclei that absorb specific radio frequencies when the nuclei are in a strong magnetic field. Only nuclei with nuclear spin work in NMR spectroscopy. For example, protons and carbon-13 each have a spin of a half, either plus a half, spin up, or minus a half, spin down. Only nuclei with an odd number of protons and or neutrons have spin and can be detected by NMR spectroscopy. For example, carbon-12 has 6 protons and 6 neutrons, so it cannot be detected by NMR spectroscopy, whereas carbon-13 has 6 protons and 7 neutrons, which is an odd number, and that's detectable by NMR spectroscopy. Nitrogen-14 has 7 protons, which is odd, and 7 neutrons, also odd, and is also detectable by NMR spectroscopy. Radio absorption by nuclei, that is, nuclei with a spin, requires a strong magnetic field. Why is that? Well, nuclei with a spin are like tiny little bar magnets. When there's no magnetic field, they have the same energy. But when you apply a magnetic field, then the orientations of those little bar magnets matters. Either they can oppose the magnetic field and thus are working against it, that would be higher in energy, or they can align with the magnetic field, which would be lower in energy. That creates an energy difference, delta E, which is defined by the equation gamma, which is a constant for each nucleus, times H, Planck's constant, times the strength of the magnetic field, B naught, divided by 2 pi. Now, in terms of calculating the frequency of the photon needed to bridge the energy gap, you can calculate that from delta E equals h nu, which is the energy for a photon. Nu represents the frequency of the photon. Now, nu will equal gamma times h times b naught over 2 pi. And you get that simply by replacing delta E with the equation that we saw before and dividing both sides by h, Planck's constant. Since gamma is unique to each nucleus absorbs radio at a different frequency in the same magnetic field. For example, a proton has a gamma of 267.53 radians per Tesla. And in a 9.5 Tesla magnetic field, which is pretty typical for your standard workhorse NMR spectrometer, the frequency for that proton absorbing radio is 400 megahertz. Carbon-13 has a gamma that's much smaller, it's 67.28 radians per Tesla. So in the same magnetic field strength of 9.4 Tesla, the frequency of radio absorbed by carbon-13 is 100 megahertz, 1/4 that of a proton. Nuclei and molecules have electrons around them, and electrons also have spin, but their spin opposes that of the nuclei, so that causes shielding of those nuclei from the external magnetic field. For a constant magnetic field, this shielding effect creates different radio absorption frequencies for different chemical environments. For example, different functional groups near a proton, or different atoms attached to the proton. So now we define a term, chemical shift, which is in parts per million, or delta. And that's a measure of shielding effect versus some standard. Typically, that standard is TMS, with a reference of 0 parts per million. Chemical shift is used as the x-axis in an NMR spectrum. Here's TMS, which is known as tetramethylsilane. The silicon atom in TMS gives the carbon a partially negative charge. And that's because silicon is less electronegative than carbon. That shields the protons a lot more than most organic compounds. So, its chemical shift position is set at 0. Compounds with a higher or positive chemical shift are more deshielded than TMS. That is, electron density is lower around the protons than in TMS. Lower or negative chemical shifts are more shielded than TMS. Examples would be organometallic compounds, where the metal-carbon bond puts a lot of electron density around the carbon and thereby puts a lot of electron density around nearby protons, causing more shielding. So chemical shift is defined as the frequency of a nucleus in Hertz minus the frequency of TMS in Hertz divided by the spectrometer frequency in megahertz. Since you have Hertz divided by megahertz, and megahertz is 10 to the 6th Hertz, that's why chemical shift is defined as parts per million. 10 to the 6th is a million. Since chemical shift is a ratio, the values are all the same for NMR spectrometers of any type, and they're obtained experimentally. You use a chemical shift table to predict what a nucleus, for example a proton, is attached to. For example, H attached to C, which is attached to F, has a chemical shift region between 4.2 and 4.8 parts per million, whereas H attached to C attached to OH has a chemical shift range of 3.2 to 3.6 parts per million. Notice that the partial positive charge is higher on the carbon attached to the fluorine, and thus there's de-shielding, greater de-shielding of the proton, which is why it has a greater chemical shift than when carbon is attached to oxygen. Right now, let's focus on chemical shifts in proton NMR spectroscopy. There's a link to the table, Table 1, Chapter 11, giving approximate proton NMR chemical shift values in the video description. Let's examine how to read Table 1, the approximate chemical shift values. We have 3 examples. In our first example, you see that there's an H attached to carbon, which is attached to C double bond O, and then that C in C double bond O is attached to OR or OH. So this is an example of how to read that from left to right, and the drawing shown more explicitly depicts all of the bonding, a little easier to interpret. The chemical shift range is from 2.0 to 2.5 parts per million. In our second example, which is really an isomeric version of the first example, we flipped it around. Now H is attached to C, which is then attached to O, then C double bond O, and then that final carbon is attached to R. R represents some other carbon group. The chemical shift values are much higher, from 3.6 to 5.0. And the reason for that is that carbon is now directly attached to oxygen, which gives that carbon a much larger partial positive charge, de-shielding the proton more, giving it a higher chemical shift range. And finally, in our third example, we have H attached to AR, and AR is not argon. Okay? AR is a benzene ring. It's a symbol for benzene. And that has a chemical shift between 6.0 and 8.5. The H to AR chemical shift range is extremely valuable for figuring out molecular structure, so you want to pay attention to that one quite a bit. Let's take a look at the chemical shifts of each unique set of protons found in the compound methylpropanoate. Protons in the CH3 group attached to oxygen, which we'll label HA, are the same as H attached to C attached to O, which is attached to C double bond O, and that carbon is attached to R. This is an ester, and the chemical shift range is between 3.6 and 5.0, as you can see for that peak. For the protons designated HB, now we have H attached to C attached to C double bond O, and then that carbon is attached to OR. That's the isomeric version of the previous ester. Now the chemical shift is much smaller, ranging from 2.1 to 2.7 parts per million. And then finally, with the protons designated HC, and the methyl group at the very far left of the molecule, we have H attached to C attached to R, which is just some alkyl group. And that has the lowest chemical shift between 0.9 and 1.5 parts per million. To analyze a sample in an NMR spectrometer, if it is solid or liquid, you have to dissolve it in an NMR solvent. NMR solvents have all of the hydrogens replaced by D, which is deuterium, an isotope of hydrogen, with 1 proton and 1 neutron. Deuterium absorbs at a different frequency than a proton, so it doesn't interfere with the spectrum in proton NMR spectroscopy. For example, CdCl3 is chloroform D. We've replaced all the H's in chloroform with a deuterium nucleus. There is a residual peak, however, at 7.26 parts per million for CHCl3, and that's an impurity. We use this impurity as a reference when we don't want to have TMS as a reference inside our NMR tube. Sometimes the chemical shifts in your proton NMR spectrum are way off, nowhere where you expect them to be. And that's when we have to do the following. We have to calculate chemical shifts. More than one functional group within 3 bonds of a proton, or any nucleus, will have an additive effect on the chemical shift that can be calculated from a table. Table 2 of alpha, beta, and gamma constants, which are listed in the table. The error for measuring the chemical shift this way is about 0.5 parts per million. The link to Table 2 in Chapter 11 is in the video description. So let's take a look at the 3 equations that we have to use when there are multiple functional groups near a proton. There's also an equation for just one functional group, but you can also just use Table 1. sp3 hybridized carbon doesn't have an effect on chemical shift. So whenever you see just carbon that's sp3 hybridized near a proton, we're just going to ignore it. With CH, the chemical shift can be calculated as 1.5 plus alpha, and alpha is going to be the constant for anything that's directly attached to the carbon that the hydrogen is attached to. So the X group there would be considered an alpha group, and you would look up the alpha value for that. You then add beta, so the beta constant is going to be for the group Y, which is 2 bonds away from the proton. And then you have to add the gamma constant for the group Z, which is 3 bonds away from the proton. Now for CH2, we simply modify the equation so that it's 1.2 instead of 1.5 plus alpha plus beta plus gamma. Now CH3 doesn't have an alpha value, because if it had an alpha value, it would just have one thing attached to it. So we only look at the beta and gamma effects, so groups that are 2 bonds away and groups that are 3 bonds away. And the equation is 0.9 plus beta plus gamma. And as I mentioned, you could also calculate the chemical shift for a group directly attached to a CH3, or you could just look it up on the approximate chemical shift table, Table 1. If you wanted to calculate it, it would be 0.9 plus alpha. So for example, let's take a look at the formula CH3O, CH2CH, parentheses, CH3Cl. So this, of course, is a condensed formula, which you read from left to right. If you want to calculate the chemical shift of the CH3 that's in black, that has only one group attached to it, that's the oxygen, and thus you can just use 0.9 plus alpha, and in Table 2 that alpha value would be 2.1. So we would estimate that this chemical shift for that CH3 group would be 3.0. For the other CH3, the one there where the protons are in red, now that carbon is attached to a carbon chain, so we have beta and gamma values. So then the equation is 0.9 plus 0.5 for the beta substituent, which in this case is a chlorine, plus 0.1 for the gamma substituent, which in this case is a methoxy group. And that adds up to 1.5. Now for the CH2 group, we start with 1.2, and then we add 2.1 for the alpha substituent of methoxy, and 0.5 for the beta substituent of Cl. That gives us a chemical shift estimation of 3.8. And then for the CH, we have 1.5 plus 2.2, which is for the chlorine, that's the alpha substituent, plus 0.3 for the beta methoxy. That gives us an estimated chemical shift of 4.0. Practice problem 1. Part A. Using Table 1 in Chapter 11, the link is in the video description, estimate the chemical shifts for each labeled set of protons in the structure below. In Part B, using Table 2 in Chapter 11, again, the link is in the video description, calculate the chemical shift for each labeled set of protons, HA and HB, in the structure below. At this point, you want to pause the video in order for you to work on the practice problem. Answers to practice problem 1. In Part A, the proton HA is an aldehyde with a chemical shift range of 9.4 to 10 ppm. HB represents a hydrogen atom next to a carbon next to C double bond O in either an aldehyde or ketone. And the chemical shift range is between 2.1 and 2.7. And for HC, that's the lowest chemical shift range in our table, and that's for H attached to C attached to R, where R is alkyl. And that's between 0.9 and 1.5. In Part B, when you calculate the chemical shifts, you're going to be working with CH2 in both cases. So in HA, you start with 1.2 plus 2.3, which is for the alpha group of OH, plus 0.4, which is for the beta group of CN or cyano. That gives you an estimated chemical shift of 3.9. For HB, again, we start with 1.2, but this time the alpha group is the cyano group, so that's 1.1, plus 0.3 for the beta hydroxy group, giving an estimated chemical shift of 2.6. Looking at the actual proton NMR spectrum, it's remarkably close to the calculated chemical shifts. For HA, the actual chemical shift is 3.85, and we estimate it to be 3.9. For HB, it's 2.61, and we estimated it to be 2.6, which is almost right on the nose. In addition, the OH group is found at 3.44 in the actual proton NMR spectrum. How do we know how many protons are represented by each peak or peak pattern in the NMR spectrum? We obtain this from integration. Integration is the ratio of areas under these peaks. That's equal to the ratio of the number of protons that are present. So for example, if you look at the two sets of peaks we have here, you look at the areas under the peaks, that corresponds to a ratio of 2 to 1, which would mean there would be twice as many protons in our first peak as in our second peak. In the NMR spectrum, this area under the peak is obtained as an integral, which is a trace that looks like a staircase step. The ratio of the heights of the steps equals the ratio of the areas under the peaks, which, as we just learned, is equal to the ratio of the number of protons. So if you take the ratio of the heights of these staircase steps, these integrals, we get the 2 to 1 ratio. Now, what does that 2 to 1 mean in practice? Well, for example, it could mean a CH2 is represented by the 2 and the CH is represented by the 1. Okay, let's go back and look at the proton NMR spectrum of methyl propanoate again, but this time instead of looking at the chemical shifts, we're going to look at the integration of each of the sets of unique protons. As you can see, the integration shows a ratio of 1 to 0.67 to 1. Now the reason that you're not getting a nice whole number for 0.67 is that the NMR arbitrarily decides that the first peak on the left is 1, and thus it takes a ratio from that point. So the first peak is 1, the second peak is 2/3 of that value in area, and the third peak is the same area. This doesn't tell you how many protons there are unless you know how many protons are in the molecular formula, and you use that to convert these numbers into real numbers of protons. So what we have to do is use a little algebra. From algebra, we know that we can take the 1, the 0.67, and the 1 and add them up, multiply them times x, and set that equal to the number of protons, which in this case is a total of 8. If we solve for x, we'll be able to get a multiplication factor, which will allow us to convert the original integration values, those integrals, into whole numbers of protons after we round. So 2.67x equals 8, and thus x equals 3. That's our multiplication factor. Next we take our integrals and multiply them times 3. So we get 3 to 2 to 3, which is the same as CH3 to CH2 to CH3, exactly as is found in our structure. Practice problem 2. What is the actual ratio of protons represented by the peaks in the following proton NMR spectrum? The molecular formula is C8H14O. Now remember that with integration, we're just getting the areas under the peaks. We have to use the number of protons in our molecular formula to figure out how many protons are represented by each set of peaks. And that requires using a little algebra. At this point, you want to pause the video in order for you to work on the practice problem. Answer to practice problem 2. First, you need a factor by which to multiply each integral to get a total of 14 hydrogens. Use algebra to solve the problem. So using our integral values, we have 1.03 plus 1 plus 1.45 times x equals 14. Thus 3.48x equals 14, and x equals 4.02. Now multiply each integral by 4.02 and round to the nearest whole number of hydrogens. So we get 4.02 times 1.03 equals 4.14, or 4 hydrogens. 4.02 times 1 equals 4.02, or again 4 hydrogens. 4.02 times 1.45 equals 5.83, or 6 hydrogens. So the actual ratio of protons is 4 to 4 to 6. Now you really can't have 4 hydrogens in one spot or 6 hydrogens in one spot, so there must be symmetry in this molecule. There must be 2 identical CH2s making 4 hydrogens in one area of the molecule, another 2 set of CH2s making 4 hydrogens in a different area of the molecule, and 2 CH3s making 6 protons in another region of the molecule.